Technology leaders who will build a truly
Okay. Yeah.
Good evening, ladies and gentlemen, respected dignitaries, esteemed guests, and dear friends. I'm Priya Venkat from the Office of Global Engagement, IIT Madras, and I'm absolutely delighted, and it's my honor to be your Masters of Ceremony for today's public lecture by Professor Sachdev from Harvard University. So before we begin, I would urge all of you to kindly register for the lecture. If you have already done it, please remain seated. If you've not done it, kindly proceed to the registration desk and complete the registration process. Also, ensure that your mobile phones are on silent mode. Thank you. I request all of you to kindly rise for the Tamil Thai Valthu and the Vande Mataram.
நீராறும் கடலுடுத்த நிலமடந்தை கெழிலொழுகும் சீராறும் வதனமென திகழ்பரத கண்டமிதில் தெக்கணமும் மதில் சிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை நுதலும் தரிதனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம்பியந்து செயல் மறந்து வாழ்த்துதுமே 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 வந்தே மாதரம் வந்தே மாதரம் சுஜலாம் சுஃபலாம் மலயஜ ஷீதலாம் சஸ்யஷாமலாம் மாதரம் வந்தே மாதரம் शुभ्रज्योत्स्नां पुलकितयामिनीं फुल्लकुसुमितद्रुमदलशोभिनीं सुहासिनीं सुमधुरभाषिणीं सुखदां वरदां मातरं वन्दे मातरम् वन्दे मातरम्.
So once again, a formal welcome to the Eminent Speaker Lecture Series. I would like to start off with a brief introduction or overview about the Eminent Speaker Lecture Series. This is an initiative by the Global Engagement at IIT Madras. The series aims at significantly elevating the international profile of IIT Madras, featuring renowned speakers, including Nobel laureates, esteemed scientific leaders, and notable figures across the globe. The first lecture, held in February 2024, was presided by Professor Karl-Heinrich Helden, a molecular cell biologist and cancer researcher at Uppsala University and chair of the boards of Nobel Foundation. In July 2024, we had Professor Brian Kobilka, a Nobel laureate in chemistry, and he delivered a lecture on From the Fields to Frontiers, the journey of a physician scientist. Now we all are gathered here for the third Eminent Speaker Lecture Series featuring Professor Subir Sachdev. To begin the proceedings, I would like to invite Professor Yasir Iqbal from the Department of Physics, IIT Madras, to deliver the welcome address.
Good afternoon, everyone. It's really gratifying to see so many school students and college and university students here, and more are trickling in for this program, which is celebrating in some sense 100 years of one of the most successful of all physical theories and one of the pillars of science towards understanding modern physics, and with forays into biology, cognitive science and other things being explored. And it's still standing solid, and it's only 100 years young in some sense. It's 7th January today, so I think it's a fair bet. I have not checked the chronological. This might be the first event in the world celebrating 100 years. I know there's a big event in Bangalore next week at the first conference, and it's an honor for the citizens of Chennai. It's a real pleasure, a privilege to have none other than Professor Subir Sachdev. On a personal note, he's my hero. So when I invited him and he decided to come, it was a personal joy. But for people doing us in theoretical physics, experimental physics, he's a star. So for all of us, it's a moment of joy and a pleasure. We've all worked through some of his works, which have transcended across disciplines in physics. His career started in the early 70s when he moved to MIT, pursuing a bachelor's in physics after a short stint at IIT Delhi, where he was an electrical engineer. As with many engineering people, they realize that physics is more charming. So they shift. This story of shifting from electrical engineering into physics started with Paul Dirac, as far as I know. So Professor Sachdev moved to MIT, where he did his undergrad, after which he moved to Harvard University and worked with David Nelson, looking into problems of statistical physics and their impacts on condensed matter problems, on frustrated systems and other problems of that nature. Then came the revolution of high temperature superconductivity, and he was at Bell Labs, and he moved from statistical physics to looking at high temperature superconductivity, which has had tremendous impact both in fundamental science with so much promise in the future, which I'm sure Professor Sachdev will talk about. And he's made sort of pioneering contributions to so many branches, not just of condensed matter physics, but other branches. And more importantly, has established transdisciplinary techniques across physics, and not just techniques, but really insights which are prophetic. In the early 90s, his work, which he'll talk about, I'm sure, would lead a few decades later to its unforeseen connection to black holes. So it was very sort of remarkable to see him already in the early 90s stumbling upon stuff while exploring his in his research, things which later turned out to have a connection between metals and black holes and other things. He's a prolific publisher of papers. If you check the archive, hardly a couple of weeks pass till I see a very nice paper from him. It's really remarkable. He's an inspiration for all of us as energy, and for his remarkable contributions, he's been bestowed with so many accolades, among which I would like to highlight is the Dirac Medal of the International Center for Theoretical Physics in Trieste, which has been awarded to people in the highest luminaries in science. Professor Sachdev, together with Xiaogang Wen, was the recipient of this award in 2018 for his pioneering contribution and outstanding insights into the theory of quantum phase transition, quantum phases of matter, criticality, and the connections between these. He was awarded the Lars Onsager Prize, which is the highest award of the American Physical Society. He is the recipient of many honorary doctorates, of many awards by various physical societies in the world. He's been elected to the Royal Society, UK. He's a fellow, elected fellow of the American Academy of Arts and Science. He's elected fellow of the National Academy of Sciences. And I could go on forever, but I would not like to stand between you and Professor Sachdev, and I would like to, first, before we invite, I would like to welcome him and request Professor Mahesh Panchagnula, who was a Dean Emeritus of Alumni and Corporate Relations, to please welcome him with a bouquet. Professor Mahesh and Professor Subir. So let's welcome Professor Subir Sachdev, and thank you so much for taking out the time from your visit to India to spend with us at IIT and to illuminate the citizens of Chennai on the exciting new developments that are taking place and take us through a journey of this 100 years of quantum mechanics. Professor.
Well, really, many, many thanks, Professor Iqbal, for the kind invitation to come here to Chennai. Although I now live in the United States, I come back to India at least once every year. I grew up nearby in Bangalore, went to school there, and have occasionally visited Chennai in the past. And it's amazing to see all the development here, which seems to be a lot less chaotic than in Bangalore, which has become unrecognizable to me. Anyway, okay, so let's talk about physics. So this is, as Professor Iqbal mentioned, this is a celebration of 100 years of one of the most great achievements in science, which is the development of quantum mechanics. But let me begin by talking about what happened before quantum mechanics. And in school, we all learn about Newton's laws of motion, which are actually not due to Newton. But Newton, a great achievement was what's highlighted here. He showed that the same laws of motion applied to planets moving around the sun as applied to apples falling from a tree. So there's a basic law of gravitation that controlled how the apple fell from the tree or how all the planets moved around the sun. And this led to amazing predictions, initially already to an understanding of tides on the Earth, and then many revolutionary advances are an understanding of both celestial and earthly mechanics. So this was very remarkable. You went all the way from 1 trillion meters, which is the size of a solar system or something, to 1 meter. All right, so we've gone from 1 trillion to 1 meter, and there's an amazing unification of the laws of nature between these very different scales. And this was also philosophically a big revolution, where people were now starting to understand that the laws that applied in the heavens to the gods, the planets for the gods, were the same laws that applied to humankind. And I think that was really intellectually a great part of the scientific revolution that began with Newton and others at this time. So we can keep going to smaller and smaller distances and ask, when does this stop? We've gone down from 1 trillion meters to 1 meter. What happens on even smaller distances? So you can go all the way down to the basic constitution of matter that we know today. That's the hydrogen atom. It's sort of like a mini solar system. There's the nucleus, which is very heavy and big at the center, and around which is the sun, and around the nucleus is a bunch of electrons executing orbits. And the size of the orbit we know now is very small. It's 10 to the power minus 10 meters, so it's a tenth of a nanometer. And so now you can ask, do the laws of Newton apply here? And it became clear, starting from late 19th century and then from early 20th century, when the work of Planck and so on and many others, that the answer was no. There just didn't seem to be any way that Newtonian mechanics would work all the way down to 10 to the minus 10 meters. So the answer, of course, was the final answer, and surprisingly, it was the final answer, came 100 years ago today, where Schrödinger and Heisenberg wrote down slightly different forms, but equivalent forms of the new equations of motion that were going to replace Newton's equations. Now, this new theory also had the feature that when you applied it to very big objects, like the planet or an apple, it wouldn't be very different from Newton's laws. But when you get down to very small scales, then it would be completely different. And why did everyone immediately believe that that Schrödinger and Heisenberg were on the right track? Well, because it explained some things very easily and very remarkably. It's just a very simple equation, which I haven't written out, but it explained some observations that were around for a few decades, including what's called the spectrum of hydrogen. So here you have some hydrogen gas on the left, and you send the light emitted from the gas through a prism, and you get a bunch of very sharp spectral lines across the visible spectrum and even beyond. And these occur at very, very special frequencies, which are really independent of anything. They're very characteristic of the atom that's in here, and hydrogen being the simplest atom was the one that was studied. And basically, this theory of Schrödinger and Heisenberg gave precisely the right values of all of these frequencies, and that pretty much convinced almost everybody that this was correct. But the theory was rather strange. It had, as I'm sure you've heard, of things named after these two gentlemen. There's the Schrödinger's cat, where a cat can be both alive and dead. And there's Heisenberg's uncertainty principle, which says you can't measure both position and momentum at the same time. And these are very counterintuitive things that people found very hard to accept, because they're not things that are present in the Newtonian view of the universe. And what my talk is about, and what's happened over the last 100 years, is to take this simple theory of one electron for a hydrogen atom and keep applying it to larger and larger distances, and see if new exotic phenomena appear that you wouldn't have guessed from Newtonian point of view. And my talk is really about that the answer is yes, there are many remarkable phenomena that even occur on the scale of planets, sometimes in the right circumstances, or of a big crystal, which really are a reflection of these laws of motion, which began with the description of very microscopic degrees of freedom. But we now know that these very microscopic effects can also have certain macroscopic consequences, some of which I'm going to talk about in the next few minutes. All right. So physicists being what they are, they very quickly said, okay, hydrogen is good. How about what can you do next? And so people went to helium, started talking about the hydrogen molecule, and there was slow progress, very rapid progress in some cases, and things seemed to be working very well. And so it was Sommerfeld, 2 years later in 1927, said, well, why don't we just apply it to not 1, 2, 3 electrons? How about 10 to the raised power 23 electrons? Because that's, if you have a given metal, a piece of copper, or any wire in your iPhone, it's got that many electrons in it. And can we describe all these electrons now using the same theory of Schrödinger and Heisenberg? And surprisingly, the answer turned out to be yes. There was a very simple extension. And in Sommerfeld's formulation, you have all these electrons flowing in a wire, which have been donated by by the metallic atoms. So if there's a copper wire, then the last electron in copper has been donated to move freely. And he just ignored the fact that the electrons can collide with each other. They just move on their own. And that turned out to be remarkably a very good starting point, and explained many puzzles that people had studied on the properties of materials like copper and gold and so on. Okay, so then we go from, we keep moving, I'm going to very rapidly move through 100 years then, and then go back through this again. Another big step in this line of thought of going from 1, 2, 3 to infinity was the theory of Bodian, Cooper, and Schrieffer of superconductivity. So what is superconductivity? Well, it's a remarkable property, which I will show a bit more about, where the resistance of a metal just goes to zero, strictly zero, below a certain temperature. And this superconducting metal can have many important technological applications, but it's also one of the remarkable manifestations of quantum mechanics on a macroscopic scale. And Bodian, Cooper, and Schrieffer introduced a simple new idea, in retrospect simple, which just extended the theory of Sommerfeld a little bit and showed that you could understand superconductors. But this took 30 years, but in retrospect, it could have been done earlier, I think. And then I'm jumping on to today. So in all of these previous developments, it was really as if all the electrons were not so different from the single electron in a hydrogen atom. That is, you just had a bunch of electrons moving around, and you didn't worry about all the different subtle patterns their quantum mechanics could display. You just treated them almost independent of each other. And this was very successful, but in the last few decades, it's become clear many materials and many situations of quite important, considerable importance, but this is not true. That these quantum interacting electrons can have rather strange properties, sometimes called emergent properties, which are related to quantum entanglement, which is another new concept which has no analog in Newtonian mechanics, which I will explain a little bit. And this entanglement then has many important consequences. And I'll just mention a few that I personally have been involved in, having to do with the properties of these higher temperature superconductors. Anyway, so that's just a global overview of things I'll say more about. All right, so let's then jump directly to superconductors and just tell you about some of the observational properties before trying to say a bit about how the equations of Schrödinger and Heisenberg can help us understand these materials. Okay, so superconductivity, in fact, was discovered well before quantum mechanics, which was 1925. This was 1911, where Cavalli-Onnes in the Netherlands cooled mercury down to minus 269 degrees centigrade. So this required a refrigerator as big as this room. In fact, you can go to the Leiden University now and see this refrigerator. It's behind him in this picture. And when you cooled mercury down to this temperature, it suddenly lost all its resistance to current, became a superconductor. But as I've said, it took a long time. Quantum mechanics came in 1925, and then the Bodian-Cooper-Schrieffer theory was not until 1957 before people understood what this was due to. So sometimes it really takes a while before people understand what's right there in front of them. Some remarkable phenomena that just didn't seem to have any clear explanation. However, I'm jumping forward to now 1987, where another class of superconductors were discovered. So these have some remarkable properties, the most important being that they go superconducting at a much higher temperature, of order of minus 200 degrees centigrade or so, which is much higher because you can just take liquid nitrogen, a liquid you can buy, not so expensive, and get down to such temperatures. So this is the material, yttrium, barium, copper oxide, referred to as YBCO, and it's a little ceramic. Here's a pellet of it, and there's a few crystals of it over there. And if we just dip this in liquid nitrogen, it becomes a superconductor. So here there's that pellet which has been dipped in the liquid nitrogen, which is in the car labeled 18, and it's floating above a set of magnets. Now, perhaps you can just flash there's a video here. You can click on the screen and there you go. So you just give the magnet a push, and you see that it floats above the magnets. And that's because it's been cooled below liquid nitrogen temperatures. And that becomes a superconductor, and the superconductor has the ability to basically expel the magnetic field inside it. And as a consequence, it starts floating. But once it's not a superconductor, it's not such a good diamagnet, as we say. The magnetic field can penetrate, and it just falls due to gravity. So this is you can see a very useful object here. People have visions of levitating trains and so on, which have been, sorry, can I use this? Hello? Okay. Yeah, is that better? Okay. All right, so, yeah, and so there are a few places where superconducting magnets, although not YBCO, have been used for trains, but they're not a widespread application yet. There's also talk of using superconductors for transmitting electricity over long distances with less power loss, and there have been some initial attempts at that, but it hasn't become widespread. But probably the most promising application of superconductors is as possible magnets for fusion machines. So here's on the right, the brown pieces are the YBCO magnets, and in the cavity, there's going to be some plasma of neutrons and protons and deuterons, which when confined by the magnetic field will undergo fusion and produce, as they claim, clean fusion energy, meaning there's no CO2 anyway. There are some flux of neutrinos and neutrons which can damage the material, but anyway. So this is a very promising source of green energy for the future, and it's really taken a leap forward towards realization because of the use of these high-temperature superconductors. This is from the website of a company called Commonwealth Fusion Systems, and from what I understand, there are also companies starting up in India to explore this area. Okay, but I'm not so much talking about the applications. I want to go back and try to understand the big mystery, which is why is it that this little pellet of material, when cooled to liquid nitrogen, was able to do this. Before 87, there was no way you could do this experiment. It required, just to cool the system down, you required a refrigerator as big as a room. Now you can just do it in any classroom. So that's a huge advance, and this is still the best material since 1987 for this application. So there's a lot of effort moving that direction, but we want to focus here on the dream of Schrödinger and Heisenberg, let's say, that everything we see around us can ultimately be understood by the equations of motion. That was the Newtonian view before, but we know Newtonian view failed at some point. But will this always work? And the answer is, as far as we can tell, is yes. Okay. All right, so before I go into the theory of superconductors, let me say a bit more about the theory of Sommerfeld for ordinary conductors like copper or gold. So as I showed you this picture earlier of electrons moving in a copper wire. So quantum mechanics tells us, as you may have heard, that particles have a wave-like nature. So the lambda here is the wavelength of the electron, and it's related to the momentum of the electron by this famous de Broglie relation. The lambda is h over mv. M is the mass of the electron, v is the velocity, m times v is the momentum. So lambda is h over p, and that h here is Planck's constant. So this constant had appeared earlier in Planck's study of black body radiation. I'll say a bit more about that in a few minutes when I get to the work of Bose. And it turned out that the same constant appears here, exactly the same constant. And that was, again, a sign that there was some unified theory connecting light and electrons. And just for future use, I've rewritten this equation. This is the most complicated algebra I'll use. that lambda equals h over p is the same as p equals h over lambda. Okay. All right, so electrons are quantum waves. So how do we know they're quantum waves? Well, that has to do with this famous dead cat and live cat idea, which is that quantum mechanics introduced a remarkable new idea, which is the principle of superposition. That a physical system can be superposition of two or more distinct states. And so how do we know this? Well, the way we know this is from one of the most famous experiments in physics, which is the double slit experiment. So you're sending in here an electron through these two slits coming out from the electron source, which is like a gun in the old TVs. So electrons are coming out and going through these little holes there on two slits, and then they hit a screen. So if you look at the dots on the right-hand side, that's each little electron appearing on the screen one by one. And so they seem to appear at random positions. But as you send the electrons in many, many times, you see this very regular distribution of electrons on the right. And you can understand this distribution by a very different idea. So the electrons, as they arrive, are like any particle. It's just a blip on the screen. It's like a particle has hit the screen. But if you look at this consequence of many electrons going through, the combined distribution looks very different. Looks like this has this oscillating pattern that we call a wave. And how do we understand that? Well, that is easy to understand if you think of the electron as a wave. So if this was a surface of water and you were creating waves in the water in the two slits, the two waves would propagate and give you exactly the same light and dark patterns that you see on the screen. So as far as the interference, as it's called, between the two slits, it seems as if the electron's a wave, but it arrives as a single blip. Anyway, so this experiment can be well understood in the theory of quantum mechanics, where you view the wave of the electron as an input to a probabilistic interpretation of what you see in any given experiment. Anyway, so another way to think about this is the following. You imagine that each electron has two possible states, so which is the left state and the right state. And as long as you're not looking at the slits, then as the electron goes through the slits, it's in a superposition state, which is left plus right or left minus right, depending on exactly how the experiment is being done. So that's the superposition principle, that this is allowed. In Newtonian mechanics, this would make absolutely no sense. A particle can't have two different velocities or two different positions. Here, the answer is it can. Any physical state can be superposed with any other physical state. So once you accept this, many things fall into place. All right, so that's how we know that the electrons are waves from double slit experiments. So these electrons are moving through and interfering with each other, and they're also obeying a very important principle, which is the exclusion principles. So because of the exclusion principle, the electrons are called fermions, and the exclusion principle is no two electrons can have the same wavelength. They always seem to avoid each other completely as a fundamental consequence of something very deep about quantum mechanics. And this was also postulated by Pauli in 1925, in the same year as Schrödinger and Heisenberg introduced the equation for one electron. Pauli started thinking about immediately many electrons, mostly atomic structure, and he understood that a lot of chemistry would follow if this principle was true. Okay, so now let's get to the main actors. What is Bose-Einstein condensation, and how is it connected to superconductivity? So we have understood at some simple level, a simple metal like copper, it's basically waves of electrons moving independently of each other while obeying the exclusion principle. All right, so now I have to go back to 1900 and 1905, where we now think about light. So light is an electromagnetic wave, like the light coming from the sun, and Planck was studying electromagnetic, the black body radiation, and Einstein studied what's called the photoelectric effect. And they both came roughly to the conclusion that you can think of just as the electron. I'm going backwards in history, it went the other way around. But in our discussion, just as the electron was both a wave and a particle in some way, the light is also both a wave and a particle. So light also comes in little lumps, which we now call photons. And each photon has a definite set of momenta. It has a definite momentum, p, related to its wavelength of the light. So each lump of blue light will have a slightly different momentum from each lump of red light. And the relationship is exactly the same relationship that you see for electrons, which is p equals h over lambda. So the double slit experiments gives you some value of Planck's constant, and the black body radiation gives you the same value. So that's really was one remarkable reason for people believing these advances. Okay, so we postulate that life is made up of photons with this discrete momentum. But then what happens when you have many photons together? Do they obey the exclusion principle? So it was Bose in 1924, 1 year before Schrödinger and Heisenberg wrote down their equations in Calcutta. He wrote a remarkable paper that he mailed to Einstein. And to his credit, Einstein didn't just throw it away. He read it and published it and immediately acknowledged it had something very important to say. So if you consider many, many photons, just like we've considered many, many electrons, we can ask, do they obey the exclusion principle? And Bose postulated, of course this was before the work of Pauli and Fermi, Bose postulated that they do not obey the exclusion principle, that you can put at any wavelength, you can have any number of photons. And amazingly, from this very simple assumption that you can put arbitrary number of photons at any wavelength, and also the assumption that the photons are indistinguishable. So you put one photon, if say you have two photons, and you put them in the same wavelength, you could put the first one first and the second one after, or the other way around. Those are not two different states, they're the same state. These particles are truly indistinguishable, even in principle. This is another thing that we don't have in Newtonian mechanics. If you have three marbles, I can tell which is which. Even though they look identical, I can identify which is which. In quantum mechanics, I can't. So with that one assumption, so really Bose was the first to introduce the idea and recognize the importance of indistinguishability in quantum mechanics. And with this one simple assumption of indistinguishability, he was able to derive Planck's distribution. So this great achievement, in fact, was celebrated in Calcutta a few weeks ago. I was fortunate to be present at this celebration. And this is the Planck formula on the right-hand side, which Bose derived from a completely different way using statistics. Planck just wrote this formula down as a guess to fit the experimental data. But now there was a clear-cut derivation which really in some ways introduced the idea of a photon, introduced the idea of indistinguishability, and also in a way introduced the idea that photons have spin, but that's something I won't go into. Anyway, so that's Bose's contribution, which was fundamental to the subsequent development of quantum mechanics. And then soon after, Einstein said, well, suppose there was a particle which had a mass. So remember, photons always move with the velocity of light. Light has only one velocity. So there's no mass, they just move at a fixed velocity. But suppose there was some particle, which is a boson, what we call now a boson, in contrast to a fermion, whose velocity could be smaller than the velocity of light. So v is less than c. And Einstein then realized that if you took such a particle and you reduced the temperature, then this particle will undergo what we now call Bose-Einstein condensation. What is this phenomenon? Well, what will happen is that at low temperatures, suddenly at some temperature, you'd have a huge number of them accumulating at the zero velocity point that basically would come to rest. Since the velocity need not be c, it can go down and can come to zero. So you have all these particles, they go into the zero velocity state on their own, and this is required by the indistinguishability of these bosons. So that's quite an amazing prediction. But at this point, nobody knew about any bosons which velocity could be less than c. It was just a curiosity, which people, I don't know, I think didn't pay much attention to, but Einstein published this interesting paper. It took a few years, and it wasn't until many development in the 50s and 60s that people started appreciating that this paper of Einstein is the key input needed to understand the superconductors and the superfluids. And there are also, in some sense, there are bosons in them, but they're not elementary bosons. They're not actually elementary particles like the electron. Today, we now have an elementary particle that's a boson, the Higgs boson, just discovered a few years ago, but too late for Bose to be given the Nobel Prize for it. But anyway, so what did Bode, Cooper, and Schiffer did? So what I mean, I'm using language they wouldn't use, but this is our understanding of their theory today, that each electron on its own is a fermion. But just let's imagine that the electrons form pairs, just like hydrogen atoms form pairs to form a molecule. So somewhat similar to that, say electrons, as they're moving in a crystal, start to form pairs. And these pairs of electrons at low energies look like bosons. And when these bosons all come to rest, the pairs of electrons all come to rest, you get a superconductor. So that's, in 5 minutes is my theory of superconductivity, my explanation of the theory of superconductivity. A full explanation would require, a term's worth of study in a graduate course in physics, which I'm teaching next term, so you're welcome to listen to it. But really, it's not much more than that. Of course, underlying there's a lot of equations that you can solve and make precise predictions. But the basic idea is what's on the screen here. All right, so this kind of theory, people immediately started applying this to superconductors that were out there. And it worked beautifully for mercury. Very quickly, people were convinced it's correct. And mercury, the low temperature superconductor, is described by it. But they found that much later, of course, in 1987, when YBCO was discovered, this theory simply didn't seem to work. They worked approximately in some regimes, but it really didn't explain many of the things that were going on. And since then, in the last 30 plus years, our community has been trying to make the next big advance to understand what is the origin of this higher temperature superconductivity. I think we have a pretty good idea today, and I'll give you some picture of it, but it's not at the level of what the BCS theory is today, which can be a very quantitative and precise theory that can predict almost everything you observe. We can understand many things, but we still have some ways to go. So what are some of the mysteries here of YBCO? Okay, so I'm showing here what's called a phase diagram. How am I doing on time, by the way? Yes, see, I don't have a clock here. Okay, but how much time do I have? I haven't even started my talk. Sorry? 30 minutes, great. Okay, so this is what we call a phase diagram of YBCO. On the horizontal axis is P, which is density of electrons. In this case, it's the density of electrons in a single layer. If you look at the crystal structure there, it's made up of layers of copper atoms and various other things. So I'm talking about a single layer of copper atoms. And we're interested in the density of electrons in that copper layer. So P is actually minus the density of electrons relative to some fixed density, and T is temperature. So what you see in the yellow region is the high temperature superconductor, which can exist up to 100 Kelvin, which is minus 170 degrees centigrade. But above this TC line, these blue and red regions, those are metals. So if you look at high P, you get, and you observe various properties there. Well, it looks sort of like copper or silver in many ways. The TC is still pretty high, even there, but it's not as high as it would get in the center. So you would think that in that regime, maybe some version of the Bardian-Cooper-Sheffield theory would work. And it does somewhat, but not that well. But where it completely fails is here in the middle, where we have what's called the strange metal. And in this strange metal, if you apply the theory of Sommerfeld and its descendants, it simply does not work. So it seems like the metallic state, before the electrons start to pair up and become bosons, when they're still fermions up there, and the electrons are still fermions, they're not obeying the theory of fermions that had been so successful for the past 50 years and more in almost any material. Here it just doesn't seem to work. Fermions moving around doing things that don't look like what Sommerfeld told us they should do. And one indication of this is this famous plot of the resistance as a function of temperature. Down here near 40 Kelvin is the superconducting transition, where the red line dumps down. That's the onset of superconductivity. But at higher temperatures, you have this linear dependence on temperature, and that's very, very unusual, and one indication of the presence of this strange metal. Okay, so what is the origin of the strange metal? We're still arguing about that a bit in our physics conferences, but I think everyone agrees that in some level, there's one key ingredient that's missing from the Sommerfeld theory, and that's entanglement. So that's what I want to explain now. What is entanglement? I should emphasize, it's once you accept Schrödinger's equation or the Heisenberg equation, entanglement is an inevitable consequence. You can't avoid it. But it's a very surprising consequence, which is even most different from Newton and the Newtonian theory. So it took a while for people to appreciate that we should take this consequence theoretically seriously, because all the experiments people were studying, it didn't seem to make much of a difference. All right, so but now no one is skeptical about entanglement being an unimportant feature. It's at the center of physics today. So one can, again, view the start of entanglement by yet another paper by Einstein, the famous Einstein-Podolsky-Rosen paper. This is in 1935, 10 years after the invention of quantum mechanics, when Einstein was now already in the United States, escaping Germany. And along with Podolsky and Rosen, he wrote this paper saying that, can the quantum mechanical description of physical reality be considered complete? And what he pointed out, and he didn't say explicitly quantum mechanics is wrong, but he said that, okay, let me take Schrödinger and Heisenberg completely seriously and imagine they're always correct. And this predicts some really bizarre phenomena that I can't believe will actually be observed. And certainly in 1935, they had not been observed. So let me quickly explain what those phenomena are. So you take a hydrogen molecule, and here's a very simple picture of a hydrogen molecule, just 2 electrons, which are shown on the left, and the electrons are little arrows, and think of the arrows as the spin of the electron. So the electron is spinning on the axis, just like the Earth spins on its axis, but because of quantum mechanics, it has only 2 possible spins, either clockwise or anti-clockwise, and those are represented by the up and down arrows. So the net spin in a molecule is 0, and this can happen in 2 ways. It can happen if the first electron is clockwise and the second electron is anti-clockwise, or it can happen if the first electron is anti-clockwise and the second is clockwise. So physicists immediately realized this, and they started trying to write down, solve Schrödinger's equation and determine the lowest energy state of a hydrogen molecule. And they found that the lowest energy state was the state shown here. It's a superposition. It's a superposition of up, down, minus, down, up. In fact, the minus comes in because that's the state that has the lower energy. So this was the conclusion, inevitable conclusion of Schrödinger's equation, that a hydrogen molecule should be this kind of superposition of two different electrons. So what did EPR say? Well, EPR said, well, imagine I could take these two electrons and separate them without disturbing their spin. So I have some hypothetical agent who can come in and separate the two electrons by applying some forces, but being very careful while applying those forces to not disturb the spin. You only couple to the center of mass, but not to the spin. So if you can do that, you could take one electron and put it here in Chennai, and the other electron in principle could be anywhere. It could be in Bangalore. And you haven't disturbed their spin. Since you haven't disturbed their spin at all, the conclusion would be that they're still in this state, this superposition state. That is, if this electron on the left there is a very faint red light, you can't see it, is clockwise, and the one in Bangalore is anti-clockwise. But there's another state, which is macroscopically distant, even though they're still far away, where this one is anti-clockwise and the other one is clockwise. And before you have looked at the electrons, before you have even done anything to look at their spin, the answer from quantum mechanics is both. So you can have a superposition state, not in just some very microscopic molecule or some very close slits in the double slit experiment. You can have a superposition between Bangalore and Chennai. It's allowed. And this is very remarkable because this means that this electron here is both up and down, and that electron there is both up and down. And I don't know which is which. But if I look at this electron, I'm going to see either up or down. I don't know which one, but just like when the electrons are going through the double slit, I couldn't predict exactly where they're going to hit the screen. Here I can't predict what I'll see. But if I see down, then I know for sure my friend in Bangalore has up, and vice versa. So there's some very strange thing going on where the measurement of this electron on the left is determining what my friend very far away is going to see, or vice versa. In fact, I have no idea if the person has seen their electron or not. It won't affect, as far as I'm concerned, what I'm seeing. But once we have both done the experiment, we can talk to each other, and we can say, yes, yeah, if you saw up, I saw down, and vice versa. We never both saw up. That won't happen if you did the experiment correctly. Okay, so that's entanglement, and it's often called spooky action at a distance. And I've often wondered if Einstein actually said this. The answer is he did say it, but in German, in a letter he wrote to Max Born much later in 1947, where he said that I cannot seriously believe in quantum mechanics because because physics should represent a reality in time and space free from spooky action at a distance. All right, so it seems like this doesn't, Einstein had the intuition that there must be something wrong with this theory, but he couldn't point out exactly what was wrong. He was certainly one of the best physicists in the world, and he fully understood all its great successes, only a small fraction of which I've described to you. Every other thing that people have looked at worked, so it's hard to imagine there was anything wrong. You have to preserve all the successes while explaining this. And nobody really found a way to do that in any convincing way. Okay. But now we don't have to bother because indeed this is correct. This actually does happen. So this was a headline in New York Times about 10 years ago. Sorry, Einstein, experiment suggests spooky action is real. Okay, this was 10 years ago where people took photons, not electrons, because it's a lot easier to do this experiment in photons. And now the analog of spin is the polarization of the photon. So they have two photons which are 1.3 kilometers apart. Now this is a routine experiment done everywhere. I know there's a group in Chennai doing things like this, where you can entangle, as we say now, photons very far apart and really see that quantum entanglement is real. Okay, so Einstein's misgivings aside, nothing he said was wrong. He just didn't like the result. Well, sorry, as the headline says, we just have to accept it. This is the way the world is, and we don't have to look for another theory which will explain every other experiment and avoid this. In fact, it doesn't avoid this. Their paper was correct in the sense they showed that it is almost unavoidable that the theory of Schrödinger and Heisenberg would lead to this bizarre effect, and the bizarre effect does happen. Okay. All right, so that's enough for 2 electrons. So now, now let's keep going. Just like Sommerfeld went from 1, 2 to infinity with the Schrödinger equation, let's do the same, but now allow for entanglement. Can we understand entanglement and the different possibilities of entanglement for millions of electrons? The short answer is we don't have a full understanding, anywhere close to a full understanding. And many physicists are working on different patterns of entanglement that can emerge on macroscopic scales. I'm just going to show you one very simple one, which is turning out to play, I think, a significant role in understanding the high temperature superconductors and also, surprisingly, black holes. All right, so this model that is now called the SYK model, initially it was very much motivated by work I was doing in '92 with my first student, Jin Mouye, where we were looking at the superconducting data and the strange metal data and saying, this is really bizarre. It seems hard to understand. So can we find a very, very simple model which will have some of the features which we can solve in a reliable way? So let me describe the version of that model. I'll do it in a minute. But before I get to that, we can actually in some way see that the idea of entanglement goes way back to 1865, where Herchel proposed, due to a dream of a snake seizing its own tail, the structure of benzene. So benzene consists of 6 carbon atoms, which form 3 double bonds. And if they formed double bonds in this configuration, the carbon atoms would not be in a perfect hexagon. They could also form this configuration. And Herchel postulated, well, it must be that they do both. And then it can be a perfect hexagon. So he said it resonates between these 2 configurations. And that gives you a perfect hexagon. Today we would say, yes, that's correct. It's an entanglement between 2 different configurations of double bonds of 6 electrons. So now how do we take these snakes and make them entangle millions of electrons? I can say that I had a dream, not really, which was inspired by the game of snakes and ladders. But think of each snake as going from one random position to the other, and there are electrons on this board, and the snakes are telling us which electron is entangled with which other electron. Okay, that's a joke, I hope. But this is the actual model. So imagine there are some set of sites in which the electrons sit. I'm not putting them on a square lattice, but on some random positions. And some of the electrons are sitting, the purple sites are where the electrons are. And now I'm going to allow the electrons to move around. So for example, electron 12 and 11 can move to site 5 and 14. And in quantum mechanics, every such process is associated with what we call an amplitude, which is a complex number, which is this thing on the left-hand side. And it's determined by everything, all the potentials and all the equation. If you carefully solve the Schrödinger equation, you can determine what this number is, depending on exactly where the positions are and so on, all kinds of details. So imagine this is one of the allowed processes, but there are many others, in fact, of order n to the 4, where n is the number of sites. All of these are allowed, and each of them has associated with it a complex number. And then, if I want to understand the entanglement of all these electrons, I have to take these list of complex numbers and solve Schrödinger's equation. Except that's mathematically essentially impossible, because the equation is just way too complicated to solve even in the best computers today. So you can write this down, but you have no idea what the electrons will do when they're dominated by these so-called two-body hoppings. Well, what we realized was that with one simple assumption, that these U's here are all independent random numbers, you can solve this thing. So you can actually figure out a lot about what these electrons do when they're entangled in this very simple model of random two-body hops. Okay. So what do we get? We get a solvable model where you can actually understand what Schrodinger and Heisenberg would predict for this configuration of essentially an infinite number of particles. And what we get was the exact opposite of Sommerfeld. So Sommerfeld said, hydrogen is one electron moving around, copper has 1 million electrons, but they're all just moving just like in hydrogen, independent of each other. And so there's still electrons around that you can see if you look very carefully, microscopically, that are moving through the wire. Here we say no. Actually, these electrons get all messed up, and they become essentially, they lose their identity, and they become entangled in a quantum soup. And it's this quantum soup that can carry electrons. All right, so that's a quick summary of this model. It's still not ready to explain the strange metal, and I'll say a little bit about how today we understand, starting from this work in '93, it's taken a lot of work by many people. We're getting to the point where we think we have a pretty good description of the strange metal, and it came from ideas that appeared in this model. Okay, so now let me just say a little bit about that, and I'll conclude by saying how the same model has also had an impact on some completely different field of physics, which is the study of black holes. All right, so let's go back to YBCO. And one simple picture of YBCO, due to Bhaskaran and Anderson, is very similar in some ways to the picture of Kekule that I showed you. So I remind you, I said that YBCO is made up of square lattice of copper atoms. So the copper atoms are the green sites here. And it turns out there's just one electron on each copper atom that's active. So what it wants to do is form a bond, a valence bond, just like in graphene or in benzene. And that's represented by the blue ellipse. And it's also like in a hydrogen molecule. So each blue ellipse is just like one hydrogen molecule. But now when you have lots and lots of electrons, what we see is that there's many possibilities of this sort of pairwise entanglement. In benzene, there were only 2, but here there's really an infinite number. And so this is the much more complicated state, which we now call a spin liquid, where you have entanglement over macroscopic distances. That's not a surprise, as even the EPR experiment has that. But it has entanglement over macroscopic distances of infinite numbers of electrons. So that's one possible pattern of macroscopic entanglement. It's what we call a spin liquid. It's not a metal, it's an insulator, and it's not a superconductor, but it's a starting point from understanding macroscopic entanglement, complementary to the SYK model. Okay, so how do you get a superconductor? Well, you get a superconductor by changing the density a little bit, and now these entangled pairs can move, much like the pairs of BCS. And each pair, so there's one very important difference here. See what's happening here, if you look at this picture, just as in benzene, is that the electrons are actually not moving at all. Oops. Yeah, if you look at those 4 electrons on the right, nothing moved. The only thing that moved was the entanglement. So it's a very subtle difference between those two states. It's the entanglement that's changing, but nothing's moving. So the fact that these are bosons is not important. Excuse me. Sorry. Okay. But if you make a few vacancies, then things can move. So
Now you see at the top, right, that two pairs of electrons moved from there to there. And what moved was a boson. And that leads to superconductivity. Okay. So in words, that's pretty much the right theory of superconductivity as far as we can tell today. But there's a long way between this picture and a complete theory that we'd like to have, and that's what a lot of us have been working on. And then how about the strange metal? Well, what we've shown is that if you now put in a few impurities, say you replace the copper atom by a zinc atom or something, then the physics of this entangled mess here becomes very similar to that in the SYK model, and we get a complicated entangled state which is kind of interpolates between the spin liquid physics and the SYK physics, which is actually very much like the strange metal. So that's something I'll say more about in a more technical conference tomorrow, but anyway, that's all I have to say about it today. Okay, and we wrote a paper about this in collaboration with Avishkar Patel, my former student, and How You Go, my former student, and ESLS. All right, so finally, now the last topic before I conclude. I have about 5-10 minutes, I hope. Great. So what I've done so far is introduce entanglement, a major new concept, and shown you this SYK model, which allows us to eventually understand some features of the strange metal, and macroscopic entanglement of macroscopic numbers of particles. It turns out there's a completely different system which physicists have been worrying about, the same issues, which is the macroscopic entanglement of macroscopic numbers of particles. And amazing, the type of entanglement you get in this system turns out to be very similar to that of the SYK model, and so by inference to that in the strange metal. And these are black holes. So what are black holes? So again, we go back in time. In 1916, Schwarzschild, working with theory of gravitation proposed by Einstein, which we now call the general theory of relativity, discovered that there were certain solutions of these equations which predicted some very strange stars. So if you take a star of mass m and you keep compressing it, make it smaller and smaller and smaller. Later on, it was work of Chandrasekhar, no, later. I don't know exactly when was Chandrasekhar. Before, I think it was after Schwarzschild, but anyway, yeah, I'm sure it was. Who came up with a situation where this would happen, that actually stars on their own would collapse. But at this point, nobody thought that was realistic. So you take a star of mass m, and you keep making it smaller and smaller and smaller. And what Schwarzschild found was that if it became smaller, then this radius r, which we now call the Schwarzschild radius, which is given by this very simple formula, where g is Newton's constant and c is the velocity of light, then it would become a black hole, meaning that gravity would become so strong that any light emitted by an atom inside the black hole would not escape. It would be just trapped because of gravity. So nothing, in fact, could ever escape this black hole, and it would be lost forever to the rest of the universe. The word black hole came much later, but it's what universally used. So nobody really took this much very seriously in 1916, including Einstein. But anyway, there it was. Another, just like Einstein found some amazing constants of quantum mechanics, Schwarzschild found amazing constants of Einstein's theory, and neither of which were taken seriously. They should have been, but they weren't. One of the reasons it wasn't taken seriously, this is really a ridiculously small radius. If you take the Earth and you plug it into Schwarzschild's formula, you'll get a radius of 9 millimeters. So you'd have to shrink the entire Earth to the size of a pea before it became a black hole. Why would it ever want to do that? But it's even worse than that. In fact, Einstein's theory says that once you form a black hole, the matter, gravity is, unlike other forces, gravity is always attractive. So it would just keep going forever, and that matter would collapse to a point of infinite density. And surely that's not correct. So there's a singularity inside a black hole. And so the singularity convinced many that black holes were unphysical solution of Einstein's equation and did not exist in our universe. But we now know today they're everywhere. They're in every galaxy, many in our galaxy, and every galaxy has a really huge black hole at its center, a supermassive black hole. So the Milky Way, it's called Sagittarius A star. It has a radius of 10 to the 11 meters, which is the size of the Earth's orbit around the sun. It has a mass of 4.3 solar masses. So there's a huge object at the center of the Milky Way of the size of the Earth's orbit around the sun, with a density, at least from the horizon, of what would happen if you compress the Earth down to the size of a pea. You know, it's hard to even, this boggles the mind that there's such a thing as out there, but it is. Excuse me. Okay. So that's all great, but what does that do with entanglement? Well, if you're going to take a black hole seriously and you've got matter compressed to such ridiculously high densities, you know, then you're really talking about very, very tiny distances. And surely quantum mechanics that became so important in a hydrogen atom is also important at the center of a black hole. So to really understand black holes, ultimately, we have to take quantum mechanics into account. But not many people were really worrying about these problems for quite a long time because no one had ever really seen any black holes to begin with. And it was really Hawking in 1975 who made his great contribution, realizing that quantum mechanics predicts something remarkable, that black holes are like a black body. They have a temperature and an entropy meaning there's a certain randomness associated with them, and they slowly evaporate, you know, like a cup of coffee, cools by just setting off the heat and the water evaporating. Similarly, a black hole eventually, extremely slowly, would evaporate because it's just like a hot cup of coffee, except much denser and much bigger, and the evaporation is ridiculously slow. And he even computed the temperature of every black hole, now expressed in terms, again, the same quantities you've seen before, Newton's constant, the mass of the black hole m, h bar, which is Planck's constant over 2 pi, c is the velocity of light, and kb is a ridiculous unit only because we insist on measuring temperature in units of Kelvin. If you measure temperature in units of energy, we wouldn't need it. Anyway, okay. So how can we understand this Hawking result? Well, the basic understanding is, again, entanglement. And really, you can understand the basic idea, again, by redoing the Einstein-Podolsky-Rosen experiment. So imagine I, again, have a pair of entangled electrons, and I separate them, but I put one inside a black hole. Excuse me. Sorry, I've got a little... Okay, so there's the black hole horizon. Remember, the mass of the black hole is all at the center. There's nothing at the horizon. It just kept collapsing right to the center. So as this poor electron is going past the horizon, it's lost forever. It can never come out. It's gone inside, past the horizon. It's gone. But it's still entangled with the other electron, which is in my hand, and I'm safely outside the black hole. So that electron is going out, this is falling in, and they're still entangled. All right, so that's the remarkable thing. Entanglement can persist past the horizon of a black hole. So if I'm sitting outside here with that electron in my hand on the left, sorry, on your right, then as far as I'm concerned, that electron is completely random. It's either up or down, and it's not connected via entanglement to anything in the observable universe. So, because there's quantum entanglement inside and outside of a black hole, to an outside observer, the state of an electron inside the black hole cannot be known. So the outside electron is in a random state. And what we know is that randomness is really what's responsible for temperature and entropy. And this is a very simple way of understanding why quantum mechanics, and entanglement in particular, implies that black holes have a temperature and an entropy, which was first computed by Hawking. And shown here, I forgot to mention, this is a picture of his gravestone in London, with the expression for the Hawking temperature. Excuse me, I don't know what's going on here. Okay, maybe I just take a break for 5 minutes, about 2 minutes. Okay, yeah, I'm almost done. Yes. So Hawking, as I said, gave a precise value for the temperature. He also gave a precise value for the entropy. And remarkably, this entropy, that's S, is again given by this Hawking's formula here, where A is the area of the horizon. So black holes have an entropy that's proportional to the surface area. Now this is very different from a cup of coffee or any other object we know. The entropy, or the heat they have, is proportional to the volume. But black holes' entropy has a very different origin. It's because of entanglement of these around the horizon, of these pairs that are being torn apart and which will never meet each other again. So these are fluctuations of quantum mechanics that happen on the black hole horizon. And these entangled pairs are on the surface. So it's just the surface that's giving you the entropy. And that's one way you can understand this remarkable formula of Einstein, of Hawking, excuse me. All right. So we need a much better theory for understanding not just the entropy, but the full distribution of energy states that you find near a black hole. So this is a complicated topic, but I just want to mention one region where that's been there's been quite significant advances, and that's for black holes with a net charge. And it turns out that for such black holes, you need not worry about the radial direction. All the important quantum effects happen uniformly around the sphere, and there's only a radial direction. You need not worry about the angular direction, and there's only a radial direction zeta. You can forget about x. So in the end, all of the entanglement is as if it has one point, this point zeta sub h on the horizon. And the amazing thing is you can show that the entanglement at this point is in fact described by precisely the SYK model. So this model of random entanglement of electrons or any other quantum particles, most importantly fermions. Oh, that's good, thank you. Is really related ultimately also to the same model. And this has led to a lot of advances in our understanding of the quantum structure of black holes. And let me just flash, so if you ask, the one implication of this is that if you're looking at a black hole from the outside and ask what's really inside, well, to you, it's indistinguishable from an SYK model. It's some kind of entangled soup inside, whose properties are essentially identical to those of the SYK model. And this has led to some very precise predictions. Okay, this is a way too technical a formula, but this came out of the improved understanding of the SYK model. It gives us the density of states, the number of black hole states as a function of energy for a charged black hole. Okay, so I'm done. Let me just recall, the main conclusions and the things that I've covered. So the recap is the following. So what I've talked about, the main theme of the more recent work, is how we understand and classify different patterns of multi-particle entanglement. And one of the simplest and most carefully studied, which has had impact in different fields of physics, is the SYK model. And it's a model of random entanglement, if you wish, and that really is maximal in many ways. It just becomes, things become as entangled as they possibly could, so that you can't even identify any particles anymore. In the spin liquids I mentioned there are particles, there are new emergent particles in the spin liquid. Here there's none, there's nothing. It's just an entangled soup. So that seems like rather drastic, but amazingly that has actual applications. So in one set of variables, it has helped describe the strange electrical properties of YBCO. In a different set of variables, it has led to a deeper understanding of the interior of a certain class of black holes. Thank you. I'm happy to take questions, but maybe someone else should speak for a minute or so, and then I'll feel better.
Thank you so much, Professor. Thanks a lot, Professor. That was a very insightful session. We request you to take a couple of minute rest. By the time I request the audiences to keep thinking about the questions, so we will open the floor for question and answers in a couple of minutes.
Talking a lot all yeah, okay, I'm okay. All right, let me keep going. Okay, please, I'm happy to have questions and go back or
Request the audience with questions to kindly raise your hands, and our volunteers will come to you with the microphones.
In the slide where you began to explain quantum entanglement, you actually presented the entangled particles and you actually represented the spin of both the particles.
yeah.
But the whole funda is that we don't know what the spin of the entangled particles are when we separate them. So the mystery comes when you actually try to measure it post moving them apart, and the act of measurement is what decides the the spin, and therefore the spooky action is, in fact, it happens in the act of measurement, isn't it? I mean, you in the slide you actually show it as though the up particle and the down particle are separated. That's not how it is, isn't it? And therefore,
well, on the whole, I think I don't disagree with you.
Yeah.
It's a very subtle phenomenon, and people think about it intuitively in different ways. But I want to just make clear what the experiment is, and you can interpret it as you wish. But the facts are the following. The facts is, first of all, you have to take a pair of electrons that are close to each other to begin with. So they really, and if you take a hydrogen molecule on its own at low temperatures, maybe I remove my tie. That's what it is. Yeah, that must be it. Okay. So in a hydrogen molecule, you will still get the two electrons forming this superposition. Okay. So now the spin, it's not entirely decoupled from the position. The spin creates a magnetic field, and there's various relativistic effects that couple the position of the electron to the spin. And the Earth's magnetic field is acting on the system. That's also affecting this, and there may be other fields around due to random nuclei that are moving around. So it's very important when you separate them that nothing disturbs the spin. For electrons, that's almost impossible to do because of what effects I mentioned.
How do you ensure
Yeah.
that you actually separate without disturbing the spin, which is the whole point of measuring what the state of the spin is, and therefore you don't affect it?
Well,
Isn't that the problem?
no. So this is an excellent point, and this is why it's a thought experiment, and no one has actually done this experiment. This has not been done because it is really hard to separate two electrons without disturbing their spin. But it's a good thought. So imagine you could do it by somehow turning off the Earth's magnetic field, turning off all the nuclei or something. I mean, the equations allow you to do that. So let's imagine we can do that. And then we separate them. We have electrical forces that only act on the positions but not on the spin. And then we do a very different experiment. We actually look at the spin. So now we bring in another detector and we look at the spin. And what we find is that there is definitely a correlation between what I see here and what I see there. Now you can say, that's nothing surprising. If I had a little apparatus here which somehow was designed to shoot two balls, and it's always designed to shoot a red ball on one side and a blue ball on the other side, or vice versa. So there's that apparatus sitting there and it's shooting balls, and I see I have a red ball, then I know my friend has a blue ball. I mean, what's the big deal? Right, so this is not the complete experiment. You have to do a more subtle experiment where you do many different such entanglements. And that's what leads to something called Bell's inequality, which I have not described. Only then do you really see that there's something quantum which could be realized by classical experiment. Okay, so that's a technical point I didn't go into. But so you put your finger correctly on that. Then so what's done here is precisely a measurement of Bell's inequality, which is more complicated. And here, you don't have two electrons, you have two photons. Now, photons are much better behaved than electrons. Photons have a polarization. The electric field is either rotating this way or that way. And if you create a photon and it's going down an optical fiber, you have to ensure that nothing changes its polarization. And that's very easy to do because photons don't interact with anything. I mean, their interaction with the rest of the universe under certain conditions is essentially zero. So that's why you do this experiment with light, not with electrons, because it's easy to create and move photon without disturbing its polarization. It's much harder to move an electron without disturbing its spin. So the experiments we've done with photons, we all believe it will work for electrons because everything underlying these theories I've told you is assuming it works for electrons, and it leads to predictions that are also consistent with experiments. Okay, yeah, good question.
Sir, first of all, my question is, we measure temperature of any distant object by seeing its radiation, right?
Yes, that's one way to do it, yeah.
Black hole is black. How to measure temperature of black hole?
I wish I knew. Well, you would, the way you measure, how do you measure the temperature of a black body? You send the radiation through a spectrum. You look at the distribution of light as a function of frequency, and from the shape of the spectrum, in fact, you fit the spectrum to this Bose answer that I told you about. There you go. So there's that famous formula that Bose derived from statistical considerations. You measure the spectrum as a function of nu is the frequency, and you fit it to this formula, and the fit will give you the value of T, which is the temperature.
No, fitting it is different.
Then that's what you have to do.
How will I measure? I am not getting I am not getting a photon outside from it, right?
Well, Hawking says you do. Okay. No, so the LIGO, which is now being built in India, is detecting the radiation from black holes, the gravity waves. So it's detecting gravity waves from black holes.
Okay.
But those are not yet, they're not sensitive enough to actually fit it to this formula. We don't have enough data. It's probably going to be extremely hard. I'm not optimistic it'll happen anytime soon because the Hawking temperature is very, very small. But someday we can dream that somebody builds a super LIGO that's looking at the black hole at the center of the Milky Way and measures its Hawking temperature. I mean, Hawking would surely have gotten a Nobel Prize if that had been done. It hasn't been done, but nobody believes it will happen. I mean, everybody believes it will happen. It will be correct. Yeah, it was definitely my tie. Okay. Yeah, there's a question there. Yeah. From high school students from the back, yes, please.
So, when you were explaining the Sommerfeld model,
Yes.
you mentioned how a pair of fermions can act as bosons. Like,
Yes.
How exactly is that possible?
Oh, exactly. Okay. Great question. I mean, if I just think of fermions as exclusion principle, you immediately see that can't quite be right because fermions will exclude each other. So how can you put so many fermions in the same state if they're just bound up as bosons? So great point. So that's why I was very careful to state. You may have forgotten. When I said that these pairs of fermions act like bosons, I said very carefully at low energies, where you don't have to worry about the exclusion principle. So basically the idea is the following. The exclusion principle is actually a consequence of a deeper principle. And so is the Bose statistic, concept of a much deeper principle, which is the principle of statistics. That is, if you take two fermions and you move one fermion around the other, the state of the system picks up a minus sign. So there's an anti-symmetry in the position of the state of the system when you exchange two fermions. On the other hand, for bosons, it's symmetric. Okay, so that's a more fundamental consequence. Now, when you apply that principle to free electrons, you come up with the exclusion principle. So historically, Pauli was the first to state the exclusion principle. And it's not clear who first realized that the deeper principle is anti-symmetry of the wave function. Maybe Heisenberg, maybe Dirac. It's never written down anywhere. Pauli got the Nobel Prize much later in 1940 something for the exclusion principle, but it's really not the fundamental principle. So now when we take the more fundamental principles and imagine that because of the Coulomb repulsion, the electrons are never really close to each other. They're never really in the same state. That's not the real thing. So if I have two electrons here and two electrons here, and I move them around each other, then I will see that I get two minus signs, and therefore it's actually a plus sign. So that's why. So minus times minus is plus. It's really for that simple reason. Another good question. Important point that I jumped over. Yeah, over there.
Sir?
Okay, yeah.
Good evening, sir.
Good evening.
So my question is, as we know that black hole are those which even bend space-time curve. So my question is that, is it so our planets are also moving toward the black hole because it is so denser that, is it so?
Okay, I'm not an astrophysicist. First of all, we're talking about many different scales now. So there's our solar system, which from the point of, if I was near the black hole, the solar system is a tiny point. Okay, so we think of the solar system as one body. There's no tidal forces inside the solar system to the black. The solar system itself is moving around in the Milky Way. It's had some, I forget how many years it takes to go around the Milky Way. So basically, the whole Milky Way has a rotation of all the galaxies moving around. And the center of the galaxy, like a gigantic solar system, is the supermassive black hole. Okay, so near the black hole, there's a bunch of stars. And every now and then, one of those stars, which are near the black hole, are being eaten up by the supermassive black hole. So if you look at this, I forget what the rate is. Maybe it's one every few years or something. You have to look up in Wikipedia. I remember I looked it up once. So I just said that, you know, the supermassive black hole, where is it? Yeah, as contains 4.3 million solar masses. So at some point this year, it'll become 4.3 million plus one. So it is eating up stars. They are falling in. But that's so far away, we can't really quite see the process, but maybe someday that'll be seen.
So, and what are bosons again? Like, can you tell? What are bosons basically?
Well, so quantum mechanics, the structure of quantum mechanics allows two basic types of particles. The electrons, protons, neutrons, they're all fermions. And the most important boson is the photon. So light itself is a boson. That was Bose's great discovery. And at that time, that was the only known boson. So it seemed not quite right to give it a name. Bose certainly didn't use that name. I don't know exactly when the Bose, but later on, other particles were discovered. I think the pion was probably another composite boson, which is made up of two quarks. The quark is a interior of a proton, and that's also made up, that's a fermion. Yeah.
So boson, if boson is a proton basically, so that means there'll be...
No. Boson is a photon, not a proton.
Photon?
Yes.
So there'll be more type of bosons?
No, so, if you see some light, each beam of light is made up of many colors. So you pick a given frequency. For each color, that light is coming to you in lumps. It's not, to us, light seems like it's continuous. But, so if you look at your camera in your iPhone, it's almost as sensitive to do that. It's a very sensitive camera. Even very faint light it can detect. You take a very sensitive camera like that, and you keep turning down the intensity, make the light fainter and fainter and fainter. At some point, you will see that the light is not coming continuously, but it's coming blip, 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 blip. And each blip is a boson. Each blip has a fixed amount of energy, which is Planck's constant times the frequency of the light. And it's that particle that Bose discovered, and assuming they obey what we now call Bose statistics, derived the Planck distribution formula. Yeah, question over there.
Good evening, sir. Thank you for your wonderful session.
Thank you.
My question is that if someone is interested in theoretical physics and if they want to submit any paper for review for future publication as an individual, can anyone do if they are not associated with any research institution, and how would they be able to submit their paper for a review through which mode or which organizations?
In principle, anyone can. There's no such rule.
Okay.
Every paper is refereed, and the referees are usually chosen from universities, but if it passes the refereeing process, in principle, it can be published. There's also something called archive.org, which is a much lighter refereeing, and if the paper looks reasonable, it is immediately published within a day or two. But there's also some screening process there. Just making sure it's scientific contribution. Yeah.
Okay, sir. So should the referee be chosen by the researcher who is doing, sir, or will they be chosen?
Okay, I should really have other questions on science,
okay.
But
okay, sir. Thank you, sir.
Yeah. Oh gosh. Yeah, this is, I think, the the radio. It's a bunch of radio telescopes, which are, it's an antenna as big as the Earth because it's different telescopes. So the bigger the antenna, the finer the resolution. So you go as far as the center of the Milky Way, even a radius of 10 to the 11th meters is just a tiny speck. So you need a very precise antenna to focus in. And I think this is just the radio waves coming out around the black hole. It's the view of the horizon. The scale is 1.3 times 10 to the 11 meters. It's about the size of the Earth's orbit around the sun.
Good evening, sir.
Yes.
Yeah. So I have a question. So in the case of multipartite entanglement, is it possible to deepen it using field theoretic considerations? Because
absolutely, but not in this lecture. But yes, there are many experts on that in the audience, and I invite you to come to IIT Madras and talk to some of them.
Okay, like I am already there.
Okay, great. Well, then knock on the physics department, and yeah, sure.
So, like you mentioned technical lecture that you will be delivering tomorrow. Where is it?
It's part of some conference happening. Exactly where, I don't remember.
Okay.
Yeah.
Fine.
Yeah, okay. Okay, there's a person over there who's been raising their hand over and over again. Maybe she deserves a chance here. Okay, yes, there.
I actually had one other question, but since you mentioned Hawking radiation, I would like to know your views. Like, can quantum sensors detect Hawking radiations, and if they do, then what could be the implications?
The answer to the first one is yes. I already discussed that from previous question, but it's extremely hard. I mean, it's radiation.
That's why I asked about quantum sensors, not normal sensors.
Yeah, so you could, well, I mean, LIGO is some sort of quantum sensor, but it's not detecting individual gravitons. It's a very, very low frequency radiation. So H nu is even smaller because nu is so small. To see individual quanta would be very hard, but I'm no expert on that. But anyway, so as I said earlier, no one doubts that it's there because it's sort of like entanglement, if you wish. It's just hard to believe that quantum mechanics could work in every other way and fail here. Maybe it will, but so that's why it's very important to do the experiment, to confirm that we're not being completely misguided by some reason. I don't know if it will be done in our lifetime, but maybe it will. Okay. And what would be the implication? The implication would be that this whole picture that I presented, that quantum mechanics again has won. Hawking for a while said that his result implied that quantum mechanics was wrong. 75 was when his prediction, and at that point, almost nothing was understood about many particle entanglement. But today, since we understand many particle entanglement much better, with some small contribution to the SYK model, we are pretty confident that there is no contradiction between Hawking's result and quantum mechanics. I think almost everyone believes that, but not everyone. And if such an experiment is done, hopefully that will satisfy the skeptics. But there are still skeptics who believe that Hawking radiation implies there's something wrong with quantum mechanics. But all the developments in 75 had shown that actually, again, just like in the EPR paper, it seemed like a very bizarre prediction. It's actually correct, yeah.
Actually, the other question was also a little bit technical.
Yeah.
Like you mentioned high temperature superconductors, right?
Yeah.
So can they be used in practical life? Like if they can be used in superconducting quantum computers, then obviously it could have a great impact.
Well, I think in superconducting quantum computers, we're not talking about, we're not talking about lots of currents and high magnetic fields. We're talking about very small devices which are already at low temperatures.
So that's what it could offer, right? If we could actually increase that super low temperature to actually, if we can work it out on some temperature that we could maintain. So
yeah, okay, I'm not, it's possible, I mean.
So are high temperature superconductors actually have been used in practical life in somewhere?
Right, but when you're making a qubit, it's not just the superconductivity, there's a lot of noise due to lots of other things, and you need low temperatures to reduce all the noise anyway. So that's also true, I think, of the cuprates. If you took YBCO, you would need to cool it down to ridiculously low temperatures for it to act as a reasonable qubit. So then there isn't any particular advantage, I think, of using YBCO. You may as well use aluminum because it's easier to work with, at these nanoscales.
Noise would be the problem still.
Well, you have to make these very small circuits on the micron scale, and that's very hard to do with something complicated like YBCO. You can do it with aluminum. You evaporate it with, in your nanoscience lab and make these devices. I can imagine it'd be very, very difficult to make devices with YBCO. People are working on such things, but yeah, okay.
Thank you.
Yeah.
Hello there, Professor. I want to ask about, due to the particles, the strange nature of the particles in quantum mechanics, as well as the related concepts like superposition, Heisenberg's uncertainty principle, and Schrodinger's cat, we have such strange concepts in the field of quantum mechanics. Can we conclude anything about higher dimensions or multiverses?
Oh, no.
That might be a strange question.
Multiverse is a very different thing. And I agree that if we use our classical Newtonian point of view, quantum mechanics is very strange. So everything we believe is based on experiment, which we have now accepted. So I think what the point of view is now that there's a framework for predicting the results of all types of experiments. That framework requires us to think about very strange things like wave functions and entanglement, which doesn't seem to be sitting anywhere, but is a concept that's required to understand.
But there is a certain probability that it could happen in the future, maybe.
What could happen?
The discovery of some multiverses or anything. Higher dimensions, maybe we can go further.
Maybe.
Thank you so much.
I've tried to limit myself to things that have been observed so far.
All right, thank you so much, Professor.
Sorry? Okay, fine.
So,
okay, take one more.
Yeah.
Okay.
The last question, we'll wrap the question and answer session.
So, thank you. There was a lot of excitement last year about a high temperature superconductor discovered in Korea. It was called LK99.
Yeah.
Is there some, and there's no news for a while about it. Is there something going on behind the scenes to verify that? And is it real? Second, related to that, there were a lot of people online trying very crude, I'll say citizen science experiments, trying to reproduce it, claiming they have reproduced it and so on. Do you think that is good for science as it, or was it, as some of us thought, ploy to move market prices for those metals to, because they had a lot of stock in those metals? Thank you.
Yeah, you're right in the sense that social media is changing science, and science, the way science is done hasn't evolved fast enough to keep up with it, and we have to figure out what the new standards are. With LK99, I think it's wonderful that everybody's interested in science and everybody's interested in superconductors and doing the experiments. That's all great. But that particular experiment, was not really an indication of superconductivity, and many people have confirmed that. And there are many other materials that will show similar things, which are not superconductors. These are all things that I heard about from my colleagues who are experts in superconductivity. So, and I know that many, many people, I'm sure, have tried to reproduce that LK99 experiment. And the fact that we haven't had anything further means they didn't succeed. So, yeah, this is more a comment on how science is done. When you have a negative result, you don't bother to publish it. Why bother? It's just a nuisance. And maybe we need to rethink, how in this new social media age, how to stop the spread of disinformation. In the old ways, there'd be a article in a journal, nobody would notice it, somebody would do an experiment, there'll be a conference, and everyone would agree there was a mistake, and then the authors would withdraw their paper, and fine. Today, yeah, I don't know. You're raising a good question. But the short answer is, as far as I know, LK99 has not held up. But, yeah.
Thank you so much, Professor, for your enlightening responses. Now we would to express our gratitude, we would request Professor Bhaskaran, Emeritus, IIT Madras, to felicitate Professor Sachdev.
ஸோ தமிழில் இதுக்கு பேர் பொன்னாடை போற்று.
Let me say it's a real honor for me to receive this, especially from my old friend and distinguished colleague, Professor Bhaskaran.
So I just wanted to mention something that I heard from Yasir yesterday, that apparently Subir came to Chennai in 1976 as a student and participated in table tennis game in IIT Madras, the central school, and won the match. So we're very happy to see you again here, winning many honors. Thank you very much.
I request Mr. Vinod, Office of Global Engagement, to deliver the thank you note.
Good evening, everyone. As we conclude today's insightful session of the Eminent Speaker Lecture Series 3, I would like to extend our heartfelt gratitude to everyone who have made this event a resounding success. First and foremost, we sincerely thank our distinguished speaker, Professor Subir Sachdev, for his captivating lecture on 100 years of quantum mechanics, from Bose-Einstein to superconductors and black holes. Your profound insights and passion for the subject have truly inspired us all, Professor. Our sincere appreciation goes to Professor Kamakoti Vidinathan, Director of IIT Madras, for his encouragement, as well as to Professor Raghunathan Ringaswamy, Dean, Office of Global Engagement, for his invaluable guidance and support. We extend our appreciation to Professor Mahesh Panchagnula and Professor Bhaskaran for felicitating our esteemed speaker today, sir. Thank you, sirs. My special thanks to Professor Yasir Iqbal for moderating the Q&A session and steering the discussion with such finesse, sir. Thank you, sir. I would also like to acknowledge my colleagues from the Office of Global Engagement and international student volunteers for their tireless efforts behind the scenes. Your dedication is truly commendable. Thank you so much. And a heartfelt thanks to the enthusiastic audience whose active participation underscores the significance of today's discussion, and special thanks to the media for the diligent coverage of the event, and to the technical staff for ensuring a seamless experience. Also, my thanks to online viewers for tuning in and being part of this special occasion, for those watching live on YouTube. Once again, thank you all for being here. We look forward to your continued participation in our future events. Wishing you all a wonderful evening. Thank you everyone.
Thank you, Vinod. I request you all to please rise for the national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मागे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे।
Once again, a very big thank you to Professor Sachdev for the amazing speech. I would request Professor Sachdev, dignitaries, to kindly stay back for the photo session.